Hello everyone and welcome back to my YouTube channel. Today we will be talking about the Gabriel Malonic Ester synthesis. So let me write this down first. So this synthesis is actually used to make amino acids. This is not to make an entire protein. There are other methods that scientists use and organic chemists use to make a complete protein or a peptide. This is just to make individual amino acids. So I'm going to give an overview, and I'm not going to go into the mechanism for every single step, but I will show you where the functional groups of the amino acid come from. So we begin with phthalimide. And this is a molecule that, organic chemists can buy. This is available. And so I'm going to show you how this molecule ends up being our amino acid. So first things first, we treat it with a base. And as you guys can see, this base is potassium hydroxide, which is a very small base. And the reason we need it to be small is so that it can fit into this very tight junction right here and capture this hydrogen that we have on the nitrogen, right? So that's why we need it to be a small base, not something like LDA, for example. So it has to be, it has to be concise. And KOH is pretty small, and actually it's very strong. It's a very strong base as well. So it can definitely capture that hydrogen. And as you guys can see, it leaves behind a negative charge, which is then resonance stabilized, right? So it can be on the nitrogen, as we would expect, or I know I said I wouldn't draw a complete mechanism, but I will just show you a little bit here. It can go on this carbon, and then we can have the negative charge on the oxygen as shown here, or it can be on this oxygen and vice versa, because they are equivalent. So the negative charge can go here and then that can go there. So these two are actually equivalent, and this is also equivalent to them as well. But the resonance structure that we're actually going to be using is the first one, and the reason we like this one the best is because if you guys go back to my previous videos, you will see that when a negative charge is on an electronegative atom, that electronegative atom actually wants that negative charge. So it's actually, oxygen is really happy right now. Nitrogen, on the other hand, is less electronegative than oxygen, which makes this more nucleophilic. So if you guys go back to my video earlier that I made, you will see that actually in organic chemistry, when we want something to attack, we would prefer for it to be more nucleophilic, which is why we prefer the negative charge on the nitrogen in this case and not on the oxygen. So I'm going to erase these really quickly and go back down here and show you. So this is a preparatory stage right now. All we did was add a negative charge onto the phthalimide. Next is the part where everything actually starts to form. So we're going to add a malonic ester, and this Me group just means it's a methyl group, so you guys can ignore it and just imagine there's like a methyl on here, And so here's why this is important. This ester is important because if you look down here, you see that there's a bromine. And we learned bromine is a very good leaving group because it is a weak base. So we don't want a strong base in solution. Once this dissociates, this will be Br minus, right? And that's a weak base, which is good. So this is a good leaving group. So what actually ends up happening is, before I get into that, let me go ahead and explain something about this carbon right here. And this carbon right here is very, very electrophilic. And the hydrogens on it are very, very acidic. And the reason is because it's attached, you can see, to those two carbons, which are basically carbonyl carbons, right? So this nitrogen is going to attack this carbon right here, and this Br is going to leave, right? So then this is what you see. This is this, let me use a highlighter. This is this group, and this is this group, right? And obviously, this is that, and this is that. So this actually happens in an SN2 mechanism, and SN2, if you guys can go back and watch my other video, this is actually a concerted step. So this happens all at once. There is no slow step. The slow step is the entire reaction, so this is going to be, the rate law is going to be the the leaving group as well as a nucleophile, and it's not just going to be the leaving group. So this is an SN2 reaction, which means that you're going to have a flip in the configuration. So I haven't calculated the configuration for this. If it was chiral, if this was a chiral molecule, you would flip from R to S or S to R. But that's not what we're worried about right now. Right now we're just trying to go ahead and see how this keeps on going into an amino acid. So here are the groups, and I'm glad that I kind of put them in pink and yellow. And yes, these are equivalent groups at the moment, and there's a hydrogen right here that's not shown. These groups are equivalent at the moment, but one of them will become the carbonyl, right, carboxylic acid, and the other one will become a hydrogen, and I will show you, and you will see soon why. And this hydrogen right here is important because this actually will become our R group. So this step, I'm just going to go ahead and repeat it one more time. It's kind of important. One of these is going to be a carboxylic acid. One of them will be the hydrogen that is present in all amino acids, and one of them is going to be the R group. And we will see now how that happens. So this is just another representation of it. As I said, there's a hydrogen here and there's two of them there. So that's basically what I just drew. And then we move down here and we see how we can convert this hydrogen into this R group. And from the looks of it, this R group right here, it looks like this is going to be methionine, because this is the structure of a methionine R group. But you guys can see that from this step, we can actually produce any amino acid that we want, as long as we have a good leaving group and a good carbon to attack. And I will show you how we will attack. First of all, we're going to add a base. So this is NaO methyl, but it could have been NaOH, or it could have been any small, I'm sorry, did I say this was an acid? I meant this is a base. This could be any small base that can squeeze in here and deprotonate that carbon. So it's going to take the hydrogen off that carbon. And what we're actually going to be left with, let me erase some over here, is we're going to be left with these two, after this hydrogen is gone, these two electrons. And then these two electrons, as you guys can see that this carbon is nucleophilic, it's going to go ahead here, attack this, and the bromine is going to leave. And then we have this R group attached. So you guys can see that this is the carbon that I was talking about. There's no bromine, and now we've inserted this R group onto the molecule. But are we done yet? I mean, is this like finished? No, it isn't, because first of all, we need an NH2 here, and this does not look like an NH2. This is protected, right? So we need to get rid of that protection. Second of all, we don't have a carboxylic acid and we don't have a hydrogen. So let's move on to the next step and see what happens. So now, once I add acid, H3O+, and heat, two things are going to happen. First and foremost, I'm going to get rid of my, I'm going to get rid of the protection on my NH2, so on NH2. So this, as you guys can see, this entire thing turns into this, H3N+, right? NH3+, pretty much. The other thing that's really important is this is where the heat comes in. I'm going to have a decarboxylation reaction. And I will make a video soon about the mechanism behind that one. But what's important now is that instead of having two of these groups, I'm going to have a decarboxylation reaction, and I'm actually going to have one carboxylic acid group, and it's not shown here, but I'm actually going to have a carbon dioxide leaving. So a carbon dioxide is going to actually be expelled from this reaction. And obviously, last but not least, as a byproduct of this decarboxylation reaction, I'm actually going to have a hydrogen inserted. So this very last step pretty much sets it in place. It gives me the hydrogen that I need. It gets rid of this extra group right here, and it gives me a carboxylic acid in its place. And lastly, it also just gets rid of this protecting group on the nitrogen. So I have the final product, which is an amino acid. This is my R group, this is my carboxylic acid group, this is my hydrogen group, and this is my amino group. I don't know why I did that on top of them, but I did. So this is just a summary of the Gabriel Malonic ester synthesis. So if I were to give you like a few takeaway points, something that's really important, I would say, first of all, we're going to add a base. That's a very important thing. Add base to the phthalimide. And I'll just write PTH. Right. Number 2, what you're going to want to do is you're going to want to go ahead and add an ester. But the ester has to have a leaving group at the most electrophilic carbon. Right? And I'm going to put in brackets here SN2 mechanism, just so you guys remember that, you know, this isn't something that happens over 2 steps. You're not going to have a carbocation intermediate. You're going to have it pretty much go all at the same time. And then next, what we're going to want to do is we're going to add a base again, a small base one this time, and I mean, they're both small bases. And this time what we're going to do is we're going to take, so I'm going to write remove the hydrogen, right, from the ester that we've made. And what we're actually going to do is we're going to then add the R group. And I could put this in the same step, and I probably should. So add base and then also add R group with a good leaving group. So that way you have a substitution reaction. I can say here, substitution reaction. And lastly, what we're going to do is we're going to add acid. So I'll just add H plus in heat. And that will give me, again, 2 things. First of all, I'm going to have my carboxylic acid group plus my hydrogen from the decarboxylation reaction. And second of all, it will give me my amino group. And actually, it's NH3+, but we know that's just pretty much NH2. And that's pretty much an overview of this reaction to make amino acids. So I hope that you guys understood and enjoyed this video. Please comment and like and subscribe, and yeah, like comment if there's any video in specific that you want me to cover or go over. So thank you.